Hello and good morning. Welcome to Autodesk Virtual Academy, brought to you by Cative Technologies. I'm Nigel Mbayak, Application Engineer and Customer Success Manager here at Cative as well. Today I'm joined by Nikhil Venkat. How's it going, Nikhil?
Good, Nigel. You?
I'm doing good. This is a lot better than last time when Nikhil could barely speak and still did an AVA for us with literally his phone next to his face, whispering. Man, that was
not fun. It wasn't exactly fun.
Yeah. Well, anyways, that recording is up and running, so that's good to hear. Mm-hmm. But today, we're talking about what's new in Inventor Nastran 2020.
Yep.
Some of you might be like, "What is that? What is Inventor Nastran? I know of Nastran. I know of Nastran in CAD, but I don't know of Inventor Nastran." Well, Autodesk changed the name on us to make it a little bit easier for us to understand some of these in-Canvas workflows that exist within Inventor. One of them being Inventor Nastran. So Nastran in CAD has now been rebranded in Inventor Nastran.
Mm-hmm.
HSM is now Inventor CAM, I think.
Really?
Yeah.
I believe so, yeah.
And then there's Inventor Tolerance Analysis, so on and so forth. So anyways, for those of you who are wondering exactly what we're talking about Nastran in CAD 2020, which is now called Inventor Nastran 2020. If you have any questions today, let us know in the chat or questions panel at any time. We'll go ahead and address those. Nikhil, do you have anything before we get started today?
No, other than we will go over some of the changes in 2019. So this is not a straight jump from 2019 to 2020. There were some incremental releases as well, so we'll talk about that. Won't spend too much time, but we will talk about it. We'll cover some of it.
Exactly, and a lot of people overlook this as something that they do change in those incremental updates, right? Mm-hmm. So 2019.1 is slightly different than 2019, and we kind of want to go over some of those because there are some key changes within Inventor Nastran or Nastran in CAD at that point in time. For those of you who are wondering how you get this or if I have this or not, it is included within the Product Design and Manufacturing collection from Autodesk. So if you have a subscription of like Inventor AutoCAD Vault, more likely than not, you will have Inventor Nastran. Product's already released. You can start using it.
Mm-hmm.
So if you have any questions on whether or not you actually have it, please reach out to us. We can figure that out for you. But most of our customers do have it. We just want to, broaden the knowledge base, kind of understand what's going on there. So with that, Nikhil, I will let you take over.
Thanks, Nigel. All right. Thank you all for joining. Today, as Nigel mentioned, we will talk about what is new in Inventor Nastran 2020. And as we sort of touched on already, this is not going to be what's the difference between 2019 and 2020. There were a lot of changes that happened between the two releases as well. So we'll cover some of that before we jump into what's really new in 2020. And I can tell you, some of the new features are pretty exciting. So first of all, I want to talk about what was modified, what was changed in 2019. So there were several improvements to the functionality and the workflow in the 2019 incremental releases as compared to the 2019 release. So if you didn't download some of the updates that released, for example, the 2019.1 in July, you may not see some of the new features like stress linearization, for example, which you will now see in your results environment. There's a new pin constraint type. There was a new pin constraint type that was introduced in this release. And there was also something called signed stresses for fatigue. So in a multi-axial fatigue study, you now have an option to either look at the stresses just as absolute values, or you can actually have the positive or the negative sign attached to it. Positive meaning tension and negative meaning compression. So it allows you to differentiate between the two types of stresses. Now, one of these, stress linearization, we actually covered in depth in September of 2018. We did an AVA on that specific topic. If you're not familiar with the concept of stress linearization, it's something that's pretty useful in designing pressure vessels, and it helps you specifically compare your FEA results with the pressure vessel code. There was another incremental release in October of 2018, and this was slightly less I guess it wasn't as big. So there were a couple of little additions in here. There was a new constraint type called the frictionless constraint type, and then there was a new contact type as well, which made it easier to model shrink fits and interference fits. Now between 2019.2 and 2020, there have been several new features and improvements. Most notably, of course, as Nigel already mentioned, is that this is now called Inventor Nastran. So you don't have to worry about the confusion between Nastran versus Nastran InCAD and all of that. Inventor Nastran, I think, I guess, captures more of what Nastran InCAD is about. So in addition to the usual, improvements in meshing, improvements in solver, and improvements in just general aesthetics, there's now improvements in how Inventor Nastran handles frame generator components. So if you've tried using frame generator and Nastran InCAD 2019 and previous, you would have noticed that you'll notice a few bugs. For example, when you do try and select a specific member of a frame, you may have noticed that the solid portion of that would disappear, and that you would just see the line there. So they've fixed some of those bugs. They've also fixed the bugs with the unit system. So again, you may have noticed that there were different units that were being used in different areas. So you may have set a unit system at the beginning of the analysis, but you still go into your loads and it still says Newton, or it still says kilograms, when you were really going for pound force or PSI. So those have been improved, those have been fixed as well. But the biggest improvements, the biggest enhancements come with the addition of new features. So automatic mesh convergence, hydrostatic loading, and the biggest and a really important one, I think, is Vault project management. Those are the ones that we will be covering today. So mesh convergence, hydrostatic loading, and Vault project management. And the Vault project management, again, if you've been using this for some time, that's been a source of frustration for a lot of users, because at the end of the day, Nastran does generate a whole set of files that are associated with this analysis, with a certain analysis, and managing that, manually can become really difficult, particularly considering the way the files were saved, and they would have a name that was pretty much gibberish. So that's now a lot easier to manage, and you can now manage it in using one single package file. So we'll talk about all that in detail. Let's start with the first one on there, the mesh convergence. So first of all, this is Inventor 2020, and if you haven't had a chance to take a look at it yet, you'll notice that it looks different. Aesthetically, it's different. It looks a little cleaner. So yeah, the Nastran environment also changes because of the Inventor environment. So right in your environment now, first of all, it doesn't say Nastran InCAD anymore. It says Inventor Nastran. Okay, and right here I have a pretty simple bracket. You can see it's got a few different components here. It's got two planks. It has a bushing, and it has this needle, which is going to be your load bearing component. So to start with, I will add some, I'm going to add some pretty simple constraints here. So I'll fix the bolt holes on either side of this, on either plank. Okay, and I'll fully fix those. I'm also going to go ahead and fix the translation of the base, the bottom surface of this bushing. So this is going to be allowed to rotate, but it won't be allowed to translate. Okay. Next, I want to apply a load. And in this case, I'm going to apply a moment. So under loads, if you change the type of load to moment. Then I'm going to select, actually, hang on. So this is one of those things where I didn't change the unit system. I'm going to go back and modify it. So this is Newton millimeter. I want that to be in pound force inches. Right, so I'll go back, edit my unit system to English. If I go back and add a load, notice that automatically changes to pound force. Previously, this didn't, and this is one of the bugs that's been fixed. Okay, so I will apply this moment to this the needle end here, the hole at the end of the needle, and that's going to be a moment of minus 200 about the z-axis. Okay, so go ahead, hit OK, and you see a little glyph there. It's associated, it's inside the surface, but that's essentially the direction of the load that's going to be acting on that surface. I'm also going to go ahead and modify the mesh size here. So I'll use a mesh size of 0.16 inches. And I'll modify some of these parameters, at least the element growth rate, since we have, there are a number of holes in this model. I want the growth rate of the elements to be reasonably small. Okay, so we'll go ahead and generate that mesh. And when I say element growth rate to be small, notice how the elements around the smaller hole there are actually smaller than the elements around the larger hole in the rest of the body. So that's what we mean by small growth rate. And if a growth rate were larger, then you would see a more uniform distribution of elements or between the two holes here. Okay. Now the new feature is the mesh convergence portion of it. So to back up, and if again we've talked about mesh convergence in one of the previous AVAs from last year, I believe. The mesh convergence setting in general is a measure, a metric to determine how accurate your solution is with respect to your mesh. So in general, the finer the mesh, the better the solution, the more accurate the solution. But there does come a point when refining the mesh further doesn't change the solution at all, or doesn't change it significantly. At that point, your result is a mesh independent result, or it's a mesh independent solution. And that's what we're going for, right? Previously, we would have to manually, we have a mesh size here, go in, run the analysis. You'd get some result. Now, to confirm that your mesh is accurate and your mesh is, or your solution is independent of your mesh, you would then have to go back, modify the mesh again, rerun the analysis, and then keep checking that way. And this was not an easy process. It was not a quick process. That's now a lot easier. So I can go into this convergence settings and refine the mesh either locally or globally. In this case, I'll choose local refinement. I'm going to choose the number of refinements here. Let that be 5. And I'll talk about what these different parameters mean here. So the refinement factor, or rather the refinement factor is how much you want to increment the element size by, right? So how much smaller do you want to, how much smaller do you want to make the element? In this case, I'll say I'm going to refine this by a factor of 10%. The refinement threshold, that simply represents the number of, or the proportion of elements that are candidates, I guess, for refinement. So 1 means all the elements are candidates for refinement. 0 means none of the elements are candidates for refinement. Stop criteria refers to the stop criteria and the max and the number of refinements kind of work together. Stop criteria, the percentage, refers to the the delta between the two results of two iterations, right? So if the difference is 3% or lower, then that to me for this analysis means that the solution is converged. Or it's going to run 5 refinements, whichever happens first. That's what is going to end up terminating the solution. Okay, so I'll have this as 5. I'll set up 5 refinements, stop criteria of 3%, and I'll include this in the analysis. All right. Now I'm going to go ahead and there's one thing that I forgot to do, which was set up contacts. This is an assembly, so we need to set up contacts. And now I'm going to go ahead and solve the problem. So it's a fairly simple problem, right? You've got a couple of bolt holes fixed here, and you have a simple moment acting on the other end. On the other end, it's a fairly simple problem. So this is the first time it ran the analysis. What it's doing now is remeshing and then rerunning the problem by itself. So it's going to do this 5 times or 6 times. It's going to, first of all, run the analysis once and then refine it 5 times, or until it gets to a convergence rate of less than 3%, which is what we're going for here. So it's a lot easier now to understand the accuracy of your solution, and this will kind of tell you whether or not your mesh is the source of your inaccuracy, right? Now, this convergence plot will go on until all the iterations are done. Okay, so we'll just give this a second. Okay, there we go. So it says stop criteria has been met, or the number of refinements have been attained. Right, so that finishes the refinement process. We're seeing that at time step, or at solution step 1, after you refine it the first time, the stress actually increases at whatever the highest stress point was. But subsequently, it keeps going down, and eventually the convergence rate goes to below 3%. It is negative in this case because the stress is reducing, but the absolute value is still below 3%. Okay, so this kind of gives us an idea of how good our solution is with respect to the mesh, or rather how good our mesh is for this particular problem. Right? Now you can also do this globally. So if you're not sure about the global mesh size, what we did here was local. If you're not sure about the global mesh size itself, you can change this to global refinement and run the same problem. Okay. Any questions here?
Yeah, and I think I just want to reiterate too is go ahead and just open those convergence settings real quick, Nikhil. I know that 19-year-old me, 20-year-old me, engineering student me would have made these numbers absolutely ridiculous. It would have been like number of refinements 50, stop criteria like 0.5%, right? There is a point of diminishing returns, much like increasing mesh or increasing element size, or not element size, element number.
Yeah.
There is a point of diminishing returns. You're going to get to a point where it is almost flat, and all you're doing is crushing your computer without actually getting a better answer, or an answer, better by maybe like 0.1%. So please use reasonable numbers in here. I know that, like I said, me 10 years ago would have done some ridiculous stuff in here. So I just want to make that clear as well. When people always come to me or Nikhil with like meshing questions, it's like, oh, my computer is like, it's taking me forever to do this analysis. And then we find out it's like 14 million elements or something in your assembly. Generally, you want to back that off and then slowly increase that number, which is essentially what this is doing, right? It's increasing the element number, or the mesh element number, until you get to a point where it makes sense. So, just one more time, Nikhil, can you explain the global versus local refinement?
Yes. So global versus local in this case is global refinement is just going to take the global mesh size, which is this size that we've used here. So it's gonna take that and keep reducing that size, right? Local refinement is different in that it's going to recognize the areas of highest stress and just refine those areas. So the rest of the model remains the same. For example, as we can see here, this bushing isn't really undergoing much stress. It's not really being stressed. So most of the refinement is going to happen either in this region where it's that's where the constraints are, or it's going to be in the areas of contact, because we do have some sharp corners and everything. So it's going to be in one of those two regions. So that's the difference between local and global. It's got nothing to do with the total size of the element itself, but the local refinement is going to deal with those areas of highest stress. And again, it's important to remember here that it is highest stress and not highest displacement.
Cool. Hopefully that answers that. Nikhil, can you go into the results of this and show where it actually shows the convergence stuff?
Sure. So the convergence plot, if you go into the results here, so you go to the results here, the convergence plot, you'll see that right here, right? And it's either refining these areas or it's refining those areas there. So that's the convergence. That's where you would access the convergence plot.
Yep. And if you had a percentage, obviously, where the absolute value was less, it would take longer for this thing to converge, or the mesh to converge.
Yeah. And also, if you had like a larger number of iterations, for example, it'll just keep going.
Yep. Yeah. So like I said before, don't make that number too big, at least like on the first try, right? Because we kind of have an idea. It's like, okay, the mesh needs to be refined in these areas. Maybe after this trial, we can go ahead and maybe like manually refine the mesh in those areas, or run it again with some more critical, I guess, numbers in there. Obviously not changing it too much. So I think we can keep moving.
All right. So, okay, now we have this, we have our results, we have our converged results. Now, this is going to show up as a hang on, let me find this file here.
It'll be whatever today is, right? Modified.
Yeah, it's going to be in here, I believe.
I think so.
Yeah, so there we go. So this now, the way these files are going to be saved and managed, they're going to be sitting inside the same folder that this part file with this assembly file was in, and it'll create a new folder with the same name. And you open that up, there's INCAD, there's FEA, and there's all of these different files, right? Now, all these files will have to be managed. If obviously you'd like to keep your FEA results associated with the file itself. And the easiest way to do that, of course, is managing it through the Vault. Previously, prior to 2020, that was not really possible. Inventor, stress analysis, the built-in stress analysis environment inside Inventor, that would do it through Vault directly, but Nastran just wouldn't.
Yeah, and that's just because it didn't understand the associativity between the Nastran INCAD solution files and the Inventor part assembly files.
Right. So now we have this new option here. If you right-click on Analysis, you have this new option called Create Updated Vault Package, right? And what that's going to do is it will create a new .pkg file, and there we go. So that's one single .pkg file that it creates. And when you do use the Vault to check this file in, you can then just check that in as well as an attachment. So those files are always going to be associated with each other. And also, any modifications that you make to this specific analysis, you can then just right-click and then create an updated Vault package, and it'll simply overwrite that file, the previous file. So it's now a lot easier to manage these files. You just need to manage one file now, and everything else will be associated with it, as opposed to having to manage an entire folder full of files with gibberish file names.
Mm-hmm.
Okay, so that's a huge improvement, and especially for people with large models. There are people making all kinds of complicated machines and mechanisms and all that really need an easy way to manage their files, and this now provides that, which I think is fantastic. Okay, so I believe we have a couple of questions here.
Yeah, let's take a look.
Yeah, so does that include a report file? No, it does not. So if you generated the report separately, the report you can still generate your report. That's a separate HTML file that's going to be created. But again, you can put that in the Vault, and the thing is, though, you will have to keep re-updating the report file.
Yeah, it doesn't generate the report and put it in that same folder. In this case, if you were using item-based lifecycles, I would just create that as an attachment,
mm-hmm.
And put it on the item itself.
Right. So will the Vault file contain all the results as well as the setup? Yes, it will. The setup is actually going to be contained on the CAD file itself. So this will contain all the results and everything. And when you do want to open the results, you can simply load results in here, right? So when you do load results, it's looking for .fno file. And I think this will help answer another question here as well. What does the PKG file look like? Well, think of it as a zip file. So I'm just going to open that with WinRAR, or you can open it with WinZip as well. It's the same. So it's going to have the exact same stuff. So it's going to have all your FNO files and everything. That same thing, it's just placed into this one file. Right? So think of it like a zip file, basically. Okay. There's another question here. Each Vault file for each node, which. So in general, the question here is what happens if we have multiple subcases and multiple files here. So it's going to be it'll be one PKG file per assembly, yes, but that one PKG file can contain as many things as you want. So if you had 4 or 5 different analyses here, different types of analyses, say you had a linear static, the normal modes, a nonlinear, etc. You have 4 or 5 different analysis types. You can still create PKG files and associate them with those with the CAD model. The only thing, as you can see here, the only thing this PKG file does is this package file does is it just zips everything together. It just grabs everything that's in the FEA file, in the InCAD file, and in the InCAD folder. Sorry, and it just zips it all together. So. Yeah, no matter what gets added on to this results folder, that can then be updated and added to the package file.
Yeah, hopefully that answered that question.
Okay.
And then to check this file in, you need to use the Vault client. You don't check it in from Inventor, correct?
Yes.
Yeah, so you need to go into the Vault client. You need to actually check it in, whether that's like an initial check-in or like a recheck-in. It'll look on your local working folder to find out where that is. And do it.
So let me show you how checking this file in looks like. If I can log in.
It's much more secure than mine. Mine has no passwords.
I believe I was showing somebody that they needed to use their password, and that's why I just created one.
You're probably not using a Vault project file.
Yeah, I'm not. Okay, never mind.
We can go do that later.
Yeah. Yeah, we can open this up later on. So let me just save this in the meantime. Okay. All right. Any other questions here?
I think that's it on the Vault add-in side. If anyone has any follow-ups for that, let us know via email or call us or whatever.
Okay. All right. So if you recall when I was talking about the new features, the third thing that I talked about was hydrostatic loading. Now, that's a pretty interesting feature as well. Hydrostatic loading or a hydrostatic load just means that it is the load that is being applied by water because of gravity. It's as simple as that, right? Of course, there's the pressure being applied. Now there's a big, I guess there's a big aspect to this, which is the height of the water. The water is going to contain potential energy, and that's going to be because of its height. And due to that, the pressure is actually going to vary. Now, previously, you could still do this. Some of you, if you've attended the NASA and NCAT trainings, then you may have been familiar with a water tank example where you have you have a varying pressure with height. Now, that's okay to do. There's nothing wrong with doing it that way, but it's a much more manual process, and it's a lot easier to go wrong that way. Now you have a specific load type just for a hydrostatic load. All right, so I'll set this problem up with a very simple method. Let me just modify this material. I'll pick a steel tank. Okay. For constraints, I will fix the base. So nothing complicated here until we get to the loading part of it. And also, just by the way I've set this up is that I have split this body into two, and everything in blue, that blue is supposed to represent the level of water. So on that surface that on the plane where the water ends, I have a point here, and that point is going to be representative of the surface of the water. Okay. So assign a load, and now this is the new load that I was talking about. Previously, what you would have needed to do was apply a pressure, right? But it would have had to be a variable load, and you would have had to use either a whole bunch of points here, or use an equation or something like that. So certainly not the easiest way to go about it. Now you have this hydrostatic load, which contains information like your fluid density and your load definition and all that stuff, right? So I'll select the entities to apply the load to, and that's going to be the blue surfaces here. So grab those. Okay. That should be 1, 2, 3, 5 faces. There we go. Okay. Now the next thing we want to select is a point on the fluid surface, and that's why I've created that point there. That's on the fluid surface itself, and I'm going to pick that point, and that just represents the total height of the water column, or of the water, right? So it gives us the absolute coordinates of this. Now, if you do want to modify that, you can just hit this button and change that manually. If you didn't want to place a point there as a CAD entity. You also need to select the fluid depth direction. So is it going upwards or is it going downwards? Right. So that's the fluid depth. You can always change the direction of this. So at the moment it's going to be downwards. This is what we want. Right. So it's negative y, as you can see here. And then the actual surface pressure. So is there any pressure outside of the hydrostatic pressure itself on these surfaces? I'm going to say yes. It's going to be a 200-pound pressure load on those surfaces. Okay. And then you can preview the load, and there you go. That's our hydrostatic load right there. Okay. Now once that's done, we can. The rest of the problem is pretty simple. We'll go ahead and create a fairly simple mesh here, and we'll solve the problem. So like I said previously, if you had, I believe this is one of the training examples or the tutorial examples, I'm not sure which one, but you would have seen something similar where it just the loading part of it is so difficult to handle. Okay. Now, this might seem a bit odd. I completely understand that, but that is only because we are looking at a percentage, a distorted version of the deformation. The actual displacement is 0.06, right? So it's just the two bodies are split, and that's why you see that difference there, or you see that gap. You can add a surface constraint, rather surface contact there to prevent that from happening. But yeah, this is a quick and easy way to look at what the pressure load looks like, or look at what the stresses look like. To kind of drive the point home, I'm going to create a section view here. Okay, create a section with the cut solid. And just make this a little more nicer looking. There we go. Right, so that's what we're likely to see, right? The pressure of the walls is going to be, rather if you're talking about fluid flow itself, the pressure through the middle is going to be higher than the pressure at the walls, and that's exactly what we're seeing here, right? You see the stress that's highest down the middle of this water column and lower towards the sides. And if you notice down here, even though we have a pressure load acting on the base, you see that the corners here almost have zero pressure. Okay, so super simple, quick way. This is useful for any area where you're using a hydrostatic load, right? So if you're using, say, designing something that's going to be underwater, whether you're designing a simple water tank, a pressure vessel, whatever the case may be, it's a really quick and simple way to handle and manage these loads. Any questions?
There should be a few in there, Nikhil.
Okay. Okay, so is the external pressure applied to the fluid on both the container and the fluid? So there is no fluid, there is no actual fluid here. I didn't model any fluid. All I did was change the appearance of those surfaces to blue. So it may have looked like there was fluid, but there was no actual fluid in there. So to answer the question, the additional pressure was only applied to the surfaces. Why did I use two bodies instead of just adding a split line? I did add I didn't add a split line. I believe I split the body by mistake. So that's why we have two bodies now.
If you just changed the contacts there, it would have fixed it.
Yeah, if you just add a simple contact here, that should fix the issue. So this, can you show the deformation once again? So this is the deformation. This is the actual visible deformation. If you want to look at a distorted view, you can look at a percent deformation scale. Right. So that's the only area that's being stressed, and that's why we see that kind of split there.
Yeah, but if you did a contact, then you wouldn't have that,
right?
Or
it would fix that.
Yeah.
Can this be used to simulate the effects of vacuum? I'm not sure exactly what you're looking to simulate, so I think that we can talk about that offline, Claudio. Why is there a 200-pound pressure besides the liquid pressure? Well, that's just an external pressure that we're adding, right? So there is the water. There's a pressure of the water due to the height of the water itself, and then for whatever reason we're adding additional pressure in there, right? So that's just the test condition that we have. You can also leave that zero and it'll be fine, and that'll be a pure liquid pressure problem. But yeah, this is just the test condition that we have. That's all.
Yeah, not necessary. Just something we added.
Yeah.
I think that's just about everything. Nikhil has done numerous Nashran and Kent webinars, so for those of you who haven't seen some of those, definitely check those out on our YouTube channel. I think Jessica had an announcement too. Just letting everybody know that there is an additive and subtractive manufacturing webinar up tomorrow. She put the link in the chat there. So if you are interested in that, go ahead and click that link in the Zoom chat for that information. And then Mick Hall asked a question here. Can you filter the plot to only show areas above 7,000 PSI? Absolutely.
Yep.
All you have to do is go into the results and change the boundaries for that.
Yeah, so you can go into your contour options, change, sorry about the noise, by the way. So you can specify minimum and maximum here and say 7,000 to the maximum, right? So 21,000, whatever.
Yep.
So hit display there. And there we go. So everything but 7,000 and below is going to be blue, and you only see color sort of above that.
Yeah, and you can do that with contour options for stress, safety factor, et cetera,
yeah,
displacement, so on and so forth. So yeah, super powerful. Let's see what else. Can you well, I mean, so there's a question here that says, can we see a case where the box is hydrostatically loaded from the outside? You can certainly do that.
Yeah.
We just apply it to the faces on the other side.
Right.
We won't go through that, but you can certainly apply the load to the outside of the box.
Yeah, so think about something underwater, for
Yeah.
example. That would be an example of when you would apply it on the outside.
But you would need a point at the surface of the water.
Right, exactly. So that's the only difference. So you would need a point at a certain height above that object if it's going to be submerged.
Yep. Cool. All right. I think that's just about everything. Again, thanks everyone for joining us today. Nikhil, again, thanks for going over some of this stuff in Nastran.
Pleasure.
Inventor Nastran. I'm going to get this name wrong for the
Inventor
next 3 months. For those of you who want to download this, feel free to do so from your Autodesk account. If you don't know if you have access to it, let us know. We can figure out if you guys have the Product Design and Manufacturing Collection. Anything else to add, Nikhil, before we let everybody go?
No, I think that's all I have.
Cool. Thanks, everybody. If you want to see any more simulation webinars from Kativ, let us know what you want to see, and I'll make Nikhil do it. So, again, thanks, everybody, for joining us today. We'll see you next week. Maybe we'll see some of you guys tomorrow on that advanced manufacturing webinar as well. So thanks again, everybody. We'll see you next week. Bye-bye.
Thank you all.